Hello, everybody, and good morning, good evening, wherever you are. So I'm going to talk today, as Tia mentioned, about the TensorFlow Lite implementation for RISC-V Vectors in general and for the X280 intelligence series in specifically. Before we go into the specifics of the implementation, I want to share with you the way that we kind of approach this problem. I think that the industry have been doing this kind of cycle of optimization for AI for several years now. One of the observations is that the AI models, one of the key pieces, one of the fundamental components is the neural networks. And neural networks generally are designed by a first step where you train the model and validate it in order to achieve a certain level of accuracy, which targets your solution. And this is kind of isolated totally from deploying it into the inference target devices. And this could be a lengthy process. The important part of this is that you validate that your model is actually have to achieve that accuracy, and that validation is important in means of solving the problem. After that lengthy process, the deployment on the devices are kind of isolated, and then the traditional or the well-known optimization of an iteration and performance analysis, and in many cases even tweaking the hardware, introducing new hardware block. And this cycle happens while performing this kind of targeting the inference on the edge, especially on the edge where there are constrained devices in means of power and area and cost. And we took this approach. It's with the RISC-V vectors, our implementation with the RISC-V vectors. And we basically designed the solution for the AI inference alongside the hardware. The software team and the hardware team worked in lockstep to do this design and use all the different optimizations necessary. And one of the key aspects that we came by, and these are well known, but it's good to share that and summarize these kind of general learning, is that AI models require parallel processing, such as SIMD, but also you want to have an efficient scalar process. It's not enough to have like one big parallel processing unit. It requires a lot of compute power. It has a huge demand, usually depends on the number of parameters. We see models today with billions of parameters, and things keep increasing and new models keep being introduced. And thus being able to really put on a chip or on a design or a processor core high TOPS, tera operations per second, is key to achieve an efficient inference. While we optimize and we run the end-to-end models and at the level of the application, we use the tricks like asynchronous processing. Of course, the quantization part, which basically taking the floating point training model and using a lower precision math while keeping the accuracy, is also key in order to achieve these kind of optimizations. And one of the important aspects of these is the fact that you have to do it alongside the hardware. And we'll show you later in the results, the different type of ISA implementation that we use with the RISC-V vectors and the extensions, and really optimizing this end to end. And if you look at the different techniques that we use, it basically spans all the known optimizations, and you have to really use all of these in order to achieve the performance. While doing that, we come by the advantage of RISC-V vectors, and previous speakers also talked about the RISC-V vectors and their advantages and characteristics. And one of the key aspects that we see it important to note here is the fact that it's not what we are showing here is not the first solution that run TensorFlow Lite or any inferencing framework, but really there is a lot of solutions out there with custom ISA or special hardware there's really a lot of fragmentation in means of what ISA you want to target when you implement these solutions. And we believe that the RISC-V vectors is a unifying theory around this domain. It simplifies the software development. People can reuse the work from the ecosystem. The LLVM support for intrinsics for RVV and auto-vectorization for RVV is there. We use it, we contribute, and other players also contribute to that. And there are other aspects of the RISC-V vector specification that make it really superior, which is important for the AI. And our focus here with the TensorFlow really to focus on this AI edge, and that's the results that we're going to show you. One of them is the fact that the ISA itself is a vector length agnostic. It allows these kind of applications to be developed and then deployed across the ecosystem for a wide range of applications and tools. And it really allows you to kind of keep the applications across vendors and across vector processors. The other part of the AI inferences, it is true that you have kind of structured computations like matrix multiplication or convolution. But if you look at if you want to enable the AI on edge inference, there are different models, neural network models, there are different applications, and there's that dynamic nature of this AI requires you in many cases to change that during runtime, like the different image sizes, for example. The RISC-V vectors, in addition, allow you a comprehensive range of data types and sizes. And this is important because not everything is going to be quantized, not everything is going to use int8, floating point, and other data types are also important. And you can see that available in the RISC-V vector ISA. It really provides you this kind of baseline of implementation. I would say like this 90-10%, like you have most of the things that you have there, and then the ability to use these customized instructions and the ability to extend the ISA, which is embedded in the specification, it gives you kind of the full solution. And we have seen in one of the previous presentations about the custom instructions that they have used. We do the same thing here. And one of the key custom instructions that we use is the matrix multiplication. And for SiFive Intelligence family, we have the SiFive Intelligence Extensions, which is targeted at AI. And this is kind of the fundamental part of the RISC-V vectors, that you can have an extension that is specific for this domain. So our SiFive Intelligence has that extension, while the other SiFive performance products does not have these intelligence extensions because they are targeted into a different domain. Speaking a little bit more about this special extension, and it's important to mention this because one of the key aspects of having a successful solution is really being able to address these huge computation demand in these neural networks and making them optimal. And as I mentioned, the quantization allow you to go into this reduced precision. int8, and it's proven. We have the validation, and one of the advantages of TensorFlow Lite is that you have the validation of all these models with quantized int8, and you can run them and achieve the accuracy that is acceptable by the industry and still able to accelerate it. The matrix multiplication instruction, what we call it, the quantized matrix multiplication instruction, basically we implement a 4x8, 8x4 matrix multiplication of int8 and unsigned int8, and generates a 4x4 matrix multiplication result in a single instruction in a single cycle. We see that this kind of instruction gives us a 12x speed up over implementing it with native int8 RISC-V int8 vector processing instructions. So as I mentioned before, we have the X280 processor. It implements the RISC-V vectors. The 1.0 release candidate, I believe it's going to be ratified in the coming pretty soon, finalized and frozen pretty soon. So this is the X280 has the latest the latest vector extension implementation, alongside all these data types that the RISC-V vector specification provides, in addition to the to special data types that are commonly used in the AI domain, and of course these special instructions and that I mentioned before, and we'll show you later some of the results that showcase the value and the improvements, the performance improvements and efficiency for these instructions. One of the other key pieces about the X280 is that builds on leverages a proving scalar processing and efficient scalar processing core, and it runs Linux and fully support Linux. One of the things about TensorFlow Lite that you need to run Linux in order to run it natively and out of the box. And the scalar processing is also important for the as we mentioned, it's also if you want to run an end-to-end and have a full solution, you also need to have an efficient scalar processing. It's not sufficient to just have pack a lot of matrix Mac operations. And you can see that we have we measure the performance from in aspect of scalar performance as well as aspects of these kind of tera operations per second, and you can achieve like these leading edge performance on scalar, as well as be able to pack up to 2.3 tera operations when you're doing these int8 matrix multiplications in a design. One of the key metrics and the way that we look at a good design in the X280 for the X280 is really to measure how much you can use these kind of these tops. One of the things that we do, beside analyzing performance for many of these layers and end-to-end performance of inferencing workloads, we look at how much are we able to tune the microarchitecture, the compiler scheduler, the hand-tuned intrinsics in order to achieve that high utilization. Are we putting all these tops and we are able to use it or not? And one of the metrics is how much utilization of that you are able to achieve. And we do see that we are able to achieve in these kind of neural nets, we are able to achieve 90% utilization for these loops of quantized matrix multiplication. The other part of the X280, and this is kind of the fundamental to the SiFive design, that it's configurable. There are different microarchitecture knobs that you can configure in order to achieve a balance between where you want to be in means of power and area and performance. And it's also scalable from single core and into multiple core. I'll show later results that show some single core performance and some with different frequencies. And the fact that we are implementing the RISC-V vectors, we believe that this is an advantage because it allows you to kind of deploy it across multiple wide range of AI algorithms. The TensorFlow Lite implementation itself, the way we look at it is that it's actually part of the product. The X280 is an intelligence product for SiFive, and it comes with an end-to-end TensorFlow Lite running on Linux out of the box with all the tools, LLVM, and the latest LLVM with the RISC-V support and GCC and all the tools that comes with it with this packaged Linux and TensorFlow. And one of the things about TensorFlow is that it's provided many implementations. It's called on the TensorFlow Hub of many models in many domains, from computer vision, such as object detection and segmentation, or natural language processing, text and speech domains, and many others. And one of our approach for the TensorFlow Lite is to run it natively. Running it natively basically allows you to do things like layer profiling and benchmarking, and customers who use the developers who want to use TensorFlow Lite on X280 out of the box, they can use all these kind of performance profiling and benchmarking on their own models and try to see if it requires additional tweaks. So This approach of supporting TensorFlow Lite with RISC-V natively out of the box has a lot of advantages. It runs models out of the box whenever they are supported in TensorFlow. And our support here comes with floating point and quantized 8 bits in TensorFlow Lite, which are the two major data types that are kind of being supported across the board. And many of these library operations implemented and optimized for RISC-V and for the X280 extensions. And we really have like hundreds, 300s plus, I think maybe 320 and even more neural networks in the TensorFlow Hub that we run. Currently, we're at 90% of running all of them functionally and validated. Especially in the quantized case, you have to make sure that your quantization actually achieves the level of expected accuracy from these models. So we validate them with the standard that TensorFlow Lite provide, and that way you can see that you're achieving performance, but you are also within that accuracy that is important and critical for these kind of full solutions. I will share with you a few results that we have and on MobileNet V1 and a few other networks. The setup of this is basically running on a VCU118 FPGA, running full Linux and running full TensorFlow Lite, the same way that the TensorFlow Lite currently is available and runs on silicon. We run on FPGA. We normalize this. The numbers that you see here is normalizing of a single core X280, even though you can do multiple cores. It's a single core X280 running at 1 gigahertz. And this is basically the inferencing performance. We took one metric here just to simplify the graph, which is the frames per second. You can translate it into latency. And we can see here that there are multiple neural nets. Different neural nets have different demands in means of the compute. And as such, we have different results. We also show some part of these network. We did run them with half precision float, 16-bit float, which is available in the RISC-V extension, in addition to floating point 32, the full IEEE float, which X280 implements, and the int8 RISC-V vectors with our own extensions. And we'll talk about the difference between the native extension in the next slide. And you can see that with the quantization and the SiFive extension, you have this huge end-to-end, almost 4x improvements on the entire network. This is not singular. This is running the entire network. And you can see that in many cases, it is well known in the industry that achieving 10 frames per second is kind of a real time, because usually, if you have a video, you do it, in P frames or what's, and you can see that, for floating point implementation, sometimes you can achieve these real-time kind of limit with a single core. Again, this is a single core, one gigahertz. But in some models, in this case, like the SSD MobileNet V1, you can't. It's even with the half precision, you can't achieve that, and you really need that quantized model to go above that bar. And you can see this is an example where that's why it's very common in the AI inference on the edge to use int8 data types. As I mentioned before, this is here focusing on MobileNet V1 and showing the performance results and the scaling across different implementations. Our baseline here is RISC-V Scalar on X280. One might argue that this is just not optimized, which is true. Generally, people, when you in these kind of models, if you investing time to optimize it, just optimize for vectors. And you can see that really the vectors is kind of like 25x compared to when using float. This is a native implementation for RISC-V vectors with float with the X280 and running at 2.3 gigahertz. And you can see that you have this kind of big uplift from just using vectors and a tuned implementation of vectors. But then in order for us to go beyond that and go into the next level, our first try, and this is part of the process. We're sharing some of the information here that we had across like this optimization cycle. So we first tried with the native int8 implementation, and it didn't go that well. You got the optimization in certain area, but then there's an overhead for the quantization, an overhead of how you're handling these int8 vectors, and you can't really get above that kind of floating point performance, and you get a little bit slower even. But then when we use these specialized instructions, because you look at the code, you look at the optimization, look at how you need to make it efficiently and achieve these high efficiency rate, you can see that, you know, additional almost 4x performance gains over the floating point operations, or like the native implementations, whether a float or int implementation. And in total, you get that staggering like 100x over scalars. Which is something that you know, shows the benefit of implementing RISC-V vectors and using that ability to extend, you know, these few extensions that gives you that edge over performance. We also compared against a similar sized core, which with the floating point, and you can see that you can actually be very competitive with the RISC-V vectors due to these different characteristics that we have mentioned before. To summarize, I think that this is the proving point. The X280 intelligence is a proving point for RISC-V vectors in general, and our ability to really lead with this software-first approach to give a full vertical solution with out-of-the-box tools and running these neural network models, and this optimization for AI algorithms. And it's really clear also from previous presentation that RISC-V vectors, it's really the obvious choice for doing ML. You know, the unifying theory and consolidating the ecosystem and the tools around the RISC-V vectors. So this is really an opportunity to have that consolidation. And two nice words about the X280 intelligence is that, you know, we show these staggering results that you can see only when you have like these specialized accelerators and with this performance and efficiency achievement, and running really a full Linux with TensorFlow, running neural nets, you know, running all these models that people can train themselves and put on through the TensorFlow frameworks and run it on the TensorFlow Lite. So this is a kind of an out-of-the-box solution with the software and hardware together. Thank you very much for listening, and I guess I need to go to the Q&A.
Yes. Looks like we've got just a few minutes. So if you have any questions, please feel free to drop them in the chat or the question and answer. Looks like we've got one in the chat and one in the question and answer.
Okay, I'm looking at the question and answer now. I'll go to the chat.
Okay.
So that X280 includes all VIC instructions. So yeah, the X280 implements fully the RISC-V Vectors 1.0, the standard instruction set. For ML task, it can be also be done with a subset of extension based on. Yeah, I think that there could be some optimizations of the RISC-V vectors in means of targeting the you know, a certain maybe ML task, but you know, as we said before, this is kind of to achieve this broader. A broader solution. When you design an AI solution like the X280, which tries to target multiple domains, then you want to have these different data types. So currently the X280 is available for customers to, it's generally available since July this year. And different customers might have different use cases. And some customers might deploy it and even have their create a design around it, and their customer might run different types of workloads. So it's really you have to think about the long-term deployment, and that's why supporting multiple data types is important. There might be some places where you can maybe tweak a little bit and save some area, which we are looking in the future, but you have to support multiple data types in order to have like this general deployment. Okay, this is a good question. So we basically the Mac utilization that I mentioned, the 90% is for really the kind of what we call the hot loop. But what the numbers that we achieve is 16%. We achieve 16% for the end-to-end workload, and we're working to even optimize that further in the follow-up design. We look at competitive accelerators, like the edge TPU or whatever. It's in the same ballpark. So when you look at the end-to-end, we're kind of in the same ballpark. So yeah, it's 16% end-to-end utilization. I didn't mention that in the slide, but that if people are more interested for more like kind of different angles of these data, you can approach me and we can share more results.
Fantastic. Well, thank you so much.
I think there was one more question. I'm not sure if.
Oh.
One more question on the chat. This is from Nikolai? Okay. So Nikolai is asking, you mentioned bfloat 16. What do you think about other IEEE alternative? So I think that what we implemented is the whatever ratified. These are standard, well-known for decades formats, which is the half float and the float full IEEE support. The bfloat is something that a lot of designs that have been in processors like the TPU and the Intel AVX extension have bfloat in it, and several other solutions in this domain. So this is kind of a standard, a floating point representation that have a proof in working in practice. So that's why we supported it. I think that as we analyze more and more workloads, from the way that we approach the problem is that we look at the workload at the end to end. What's the benefit of the numerics? That's why our focus for inference actually using int8 and not bfloat to optimize these workloads. Bfloat is well regarded in the training domain. So if there are other data types that would, we see that once we tweak the design, we could use these other floating point representations. It's really about, what benefits you, what is the trade-off between the ROI, between like how much investment in the area, in the engineering complexity, and how much benefit you can get out of that. Thank you.
Thank you.